now we are setting up.
Could you release your screen? Thank you.
Thank you. Okay, so Thais, can you start?
So, thank you very much for the introduction. Good afternoon, everyone. My name is Daryl Joe Santos, and I am a graduate student in National Tsinghua University. And I would like to discuss with you our research about galaxy environments of mid-infrared galaxies detected in the North Ecliptic Pole wide field. So first, let us discuss galaxy environments. As many speakers have discussed a while ago, and as many previous studies have suggested, galaxy evolution is influenced by galaxy environment. Galaxy environment describes the vicinity of galaxies, whether they live in cluster or denser environments where there are many other galaxies surrounding them, or in less dense environments or isolation in the field. And some of the relationships that have been unveiled or still in question about galaxy environment is this. So here's an example. Star formation rate, or SFR, versus density. Many studies say that star formation rate decreases with increasing density, but at redshift approximately equal to 1, this reverses. So SFR goes up with increasing density. Some people say this is the case, some people say it's not. So there's still a debate whether which one is true or not. And actually, there's still many other relationships with galaxy environment that are not having a real consensus yet. In fact, the epoch at which galaxy environment really affects galaxy properties is still a question and a key issue in modern cosmology. That's why we want, and then I would like to emphasize the importance of looking at the infrared wavelengths in studying or unveiling the mystery of this problem. So previous studies have focused on on UV and optical wavelengths. But the thing is, star formation rate is usually happening in molecular clouds, which is comprised by dust. And dust blocks the light from the UV or optical wavelengths, rendering dusty objects to be undetectable in these surveys. However, with the infrared surveys, we can cover these dusty galaxies, because when dust absorbs light from the UV or optical wavelengths, it gets re-emitted in the mid and far infrared. So we want to look into this problem with the AKARI infrared telescope. But there's one problem with looking in the infrared wavelengths. This is because AGNs, active galactic nuclei, and star-forming galaxies, or SFGs, are both bright in the mid-infrared region where AKARI operates. As you see here, AGN have this red power loss spectrum, while star-forming galaxies have this polycyclic aromatic hydrocarbon, or PA, emission, both of which are bright in the mid-infrared region. If we look at telescopes like WISE and Spitzer, they have these gaps in their filter responses. So if we make some observations with these telescopes alone, we may not be able to distinguish properly if an object in the mid-infrared region is star-forming or AGN. But with the AKARI infrared telescope, you see here there are no gaps in its filter responses, so we have a good coverage of the mid-infrared features, making our AGN SFG diagnostics better. Now, I want to give a simple analogy about this research. So I want to give you two cities to represent denser environments and less dense environments. So I want to use Taipei as the denser environment city, and then Hsinchu, where NTHC is located, as the less dense environment. And we wanted to know what would be the properties of the mid-infrared galaxies in these cities, and how do these properties change over time. This is what we wanted to look into this project. So here's the main question. So at which epoch do we see a clear effect or dependence on environment with the properties of our mid-infrared galaxies in the NEP wide field? So we have these sub-points. So we'll look at certain groups of galaxies and see if there's any environmental dependence. So we look at galaxies of different luminosities and SFGs or AGNs. We will also look into the already known relationships between galaxies, like star formation rate, density, and star formation rate, stellar mass relationships, and how our galaxy environment of our mid-infrared galaxies change with these relations. So here's a summary of our sample selection. We calculated the environment by using density. So density is calculated by using galaxies detected in the NEP wide field with HSC. So these are optically detected galaxies, and at only redshift up to 1.2. And the density is calculated with respect to the distance from the 10th nearest neighbor. And next is we also constrain the galaxy properties of our sample using spectral energy distribution or SED fitting called SIGAL. And we made sure that these galaxies are detected in mid and far infrared bands. And yesterday, Dr. Songjin Kim discussed this band merge catalog in the NEP wide field. We make advantage of this because we have a multi-wavelength data, giving us a better constraint for our SED fitting. And overall, we have a total of 1,200 sources, approximately, at this redshift. Now, we look at the results, preliminary results to be exact, of this project. So as you see here, when we plot the histogram of galaxies in different luminosity bins, so we have the normal infrared galaxies as the faintest group, and we have ULIRGs, or ultraluminous infrared galaxies, as the brightest galaxies. We bin the sources based on their total infrared luminosity. And when we plot the histogram of their normalized density, we see that there is no environmental dependence. And we also look at the star-forming galaxies and AGNs of our sample by grouping them based on their AGN contribution fraction, which is telling us how strong the AGNs are in the galaxies. So this is an output in our SED fitting, and it is the ratio of the AGN luminosity to the total infrared luminosity. And we also have composites somewhere in between star-forming and AGN. And again, when we plot the histogram of their log normalized densities, we see that there's no environmental dependence on these groups of galaxies. Now, we look at the specific star formation rate and specific star formation rate density relation. Recall that SFR is measured in stellar mass per year, while specific star formation rate is normalized to the stellar mass. So its unit is per year only. And actually, if you look here, there's no strong trend being seen here. In fact, when we look at the Pearson correlation R values and P values, their P values are really high. So we can't say with confidence that these trends that we see are significant. However, when you look here at the high redshift parts of the specific star formation rate versus density, log density, we see that there is somehow a decreasing trend. So at high redshift, we see the specific star formation rate goes down with density. And when we look at the Pearson R values, it's negative 0.1 almost. And their P values is less than 10%. So we can say with confidence that, with at least 90% confidence, that this trend is apparent. Lastly, we look into the star formation rate and specific star formation rate versus mass relation in different environmental bits. I don't think I have much time to describe to you how we divided the sources based on their density, but you can ask some questions later if you're more interested. It's also in the backup slides. But anyways, what I wanted to point out is that here, in the local redshift bin, there's no clear discrepancy between the low, medium, and the high density bin. So they overlap usually. However, at the highest redshift bin, we see that there's a discrepancy between the blue and the red lines, which refer to low and high densities respectively. So this is clearly an environmental effect for these high redshift galaxies. and star formation rate decreases with density at a fixed stellar mass. But this is only true for our highest redshift bin. So we want to give an explanation why is this happening. So here's an analogy of why this is happening. So at low redshift, at present time, recall that star formation declines up as we go to the present time. And most galaxies, because of this phenomena, is quenched already. So environment is, the usual effect of environment is to quench star formation. But if the galaxies are quenched to begin with, then we cannot see this environmental effect anymore. Makes sense? Now, when we look at high redshift, and to be fair, our bin is from 0.9 to 1.2, wherein galaxies are still composed of quiescent and star-forming galaxies. So quenching by other phenomena is still happening in this redshift bin. And because of this, we can still see environmental quenching at our highest bin, wherein most quenched galaxies are in the denser environment, as you can see here. And most of the active star-forming galaxies are at the less dense environment. So here's the conclusion of my talk. So we answered each of the questions one by one. We saw that there is no environmental dependence when we group them into different luminosities and AGN contribution fractions. However, we saw an environmental effect for the high redshift galaxies. And for the answer to our main question, as I said, we see that environmental effects are clearer at higher redshifts for our mid-infrared galaxies. This ends my talk. Thank you very much.
Okay, thank you very much. I don't have a question on Slack. Any questions from the local audience? Or oh, there is one question for you. Sorry. Okay, we got a question. Sorry. Is the source catalog, including the AGN classification, public? Is this the TW120 AGN classification of each source published somewhere?
Okay. So thank you for the question. Actually, the catalog that I'm using for AGN classification is not public. If I go, can you open the slides? Because I can't. This one. So while they're looking at the slides, I gave a criteria for identifying star-forming galaxies from AGNs. So here, oops, you see here that there's a threshold AGN contribution fraction greater than or equal to 0.2 to identify AGNs. We have studied before in our previous group member that this criteria for SED fitting is good enough to identify AGNs in the north ecliptic pole wide field. So that's why this is what we use to identify AGNs. Yeah, but as I said, this catalog is not public because it's not really a catalog, but it's more of like a criteria for setting up which one is AGN and SFG.
So do you have AGN at Z greater than 2?
I don't have a slide to show that, but yes, we do have AGNs at Z greater than or equal to 0.2.
More questions? From local remote people? Any question? Raise your hand or speak up. No more questions? Shall we move to the next? All right, so thank you very much. Thank you, Dario. I think that the next topic, next talk will be